Okay, suppose that the series A of n converges and A of n is real and positive. Then prove that the series root A of n plus 1, converges as well. So this may seem like a tough problem, but the solution is actually rooted in very simple calculus principles. So you may look at this and wonder, what series test is supposed to help you with this? Doesn't look like you can use a comparison. No integral test will help you. What can? Well, some algebraic manipulation will actually lead to a very simple and elegant answer. So this may seem far-fetched, but consider the following expression. Square root of A of n plus 1 minus square root of A of n squared. So what information can you extract from this expression? Well, you know that the square of a real number is always equal to or greater than 0. If a real number's square is not equal to or greater than 0, it's not a real number, it's imaginary or a complex number. So given this, we know that this, which is a real number, must also be equal to or greater than 0. Okay, so we know that. Now what else can we do? Well, we can expand this. So A of n plus 1 plus A of n minus 2 root A of n plus 1 is equal to or greater than 0. Well, look at that. This term over here looks exactly like this one. So we're making progress. Now we can use some algebraic manipulation to end up with this expression. And I don't think I need to show you the intermediate steps. We have this here. So because we know that, so this means that each individual term of this sequence is always equal to or less than each individual term in this sequence. So because of that, we know that this series must be equal to or less than this series over here. Okay, so we're making progress. Now, we know that this series over here can be broken up into two different series. So okay, so what now? Well, we want to prove that this converges so that we can use a comparison test to prove that this also converges. So how do we do that? Well, we know that we know that the sum of A of n converges. So if that converges, then 1/2 must also converge. It's just as simple as that, because if we know that the sum of A of n equals a real number, then multiplying the real number by a finite number like 1/2 also leads to another finite number, 1/2 r. So we know that just multiplying a finite multiple by the series, that won't change convergence. So this term converges. Now we know that the sum of this infinite series sum from A of n, starting from n equals 1 to infinity, well, this converges. So what do we know about the convergence of this guy? Well, we know that this guy starts off at A of 2. So essentially this is just the same thing as A of n, but this minus A of 1. So essentially this is less than or equal to A of n. But that's not important. Essentially what you need to know is that removing or adding a finite amount of terms in a series will not change the convergence or divergence. So in other words, if you're just adding or subtracting just one tiny term, like A of 1, just taking that out will not change the convergence or divergence of the series. So by that logic, this must also converge. And because we're just multiplying a converging series by 1/2, this must also converge. And because we know that the sum of two converging series must also converge if, well, they're like similar enough. This may not, I don't know if it always, if the sum of two converging series leading to a converging series always holds up, but in this case, it must hold up by the linearity of series. So this also converges. Now, by the comparison test, because all the terms are real and positive, which I stated at the beginning, by the comparison test, since this is always equal to or less than a converging series, this series must also converge, thereby proving. So let me write by the comparison test. So by the comparison test, we have proved that this series converges. Thank you for watching.